Hi everyone, welcome to Chapter 13, which is Introduction to Landform Study. So we have spent all our previous time in the semester talking about what happens in the atmosphere. We are now, and what happens with water, but we are now switching to the lithosphere. So the rest of the semester, we're going to talk about landforms and how they're formed, erosion, mass wasting, a bunch of other things. So this chapter is pretty short. It just serves as an introduction to those things that we're going to talk about for the rest of the semester. And so what you're looking at here in this picture is this rock formation in Monument Valley in Arizona that I visited called the Mittens. And they're called the Mittens because they kind of look like mittens. And so we're going to talk about like how does something like that form? What happened there? How do we know what happened there to get these very unique rock formations? But first, we're going to start out with just some landscape terminology. Topography is the first one, and that is the surface configuration of the Earth. Is it flat? Is it hilly? Is it steep? Is it jagged? Etc. Um, Relief refers to the difference in elevation in an area. So if you look at down here, these rock formations, this has a lot of relief, right? There's a huge difference here in elevation. Also, landforms are individual topographic features and types of topographic features that refer to two things. So, for example, Mount Rainier, pictured here, is an individual feature, um, but it is also a composite volcano. We'll talk about volcanoes, I believe, in the next module, is a type of feature. In addition, geomorphology is the study of how landforms are created, and so we'll do a little bit of geomorphology in this class. And so you're looking at here part of the Colorado River, and you could see how over time this river has eroded away this landscape and made these deep grooves in it. So the study of how that happens is called geomorphology. Um, there's also internal and external processes that form landscapes, and we are going to talk about both of those in this class. The next chapter, we're going to talk about the internal processes, and then after that, we will switch to the external ones. And it's also important to note that these are very, very slow processes, right? Most of these we are not going to really notice in our lifetime. We're talking about things that happened over thousands and millions of years. And so if you look at geologic time, which is very, 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 very long, the Earth being about 4.6 billion years old, when you think about how long the Earth has been around, how long rocks have taken to form, and where we show up over here, it's really our window of time on this planet is just so very small compared to how long it's been around. So again, Earth is 4.5, 4.6 billion years old. Some landforms are many millions of years old. They're not billions of years old because the Earth is constantly like erasing itself and remaking itself. And so how do we know how old landforms are? There's a couple different ways. One is something called radiometric dating. And the other one is this concept called uniformitarianism. Let's see if the closed captioning can pick that up correctly. Um, and so that's the idea that we can see a specific type of rock type in one place at another place, and we can date one, we can date them both. And so we need to be able to understand rocks in order to understand how landscapes form. So here is a picture in Bryce Canyon. There's a lot of pictures in the upcoming chapters that are from my vacation going to national parks in the Southwest United States, and this is one of them. And so these landforms are called hoodoos, and we want to know, what are these rocks? How did they form? What happened here? So first we're going to talk about the Earth layers, because the Earth is in layers. We have the Earth's core, which is about 4,400 miles in diameter. There is a solid inner core and a fluid outer core right here. The mantle beyond that is about 1,800 miles thick, and it is mostly fluid, mostly magma. And then we have the crust, which is where we interact with the Earth, and that is 5 to 25 miles thick, depending on where you are. It is thinner and denser under the ocean because it has the weight of the ocean pushing down on it, and is thicker and less dense on the continents. And this idea of thicker crust versus thinner crust is going to be very important to remember when we're talking about plate tectonics a little bit later. And so, how do we know about the Earth's layers? Well, we can measure seismic waves from earthquakes, and we can measure them how they radiate through the core of the Earth. So, an earthquake can happen here, and eventually we can take measurements here and we can see how that radiates into whether or not it's going through something liquid or solid. Because remember, we're not able to dig down to the core of the Earth, right? We're only able to dig into the crust. But this is how we know that this happens. And so if we watch that animation one more time, hopefully it'll go. Let's see if I can go back and forth. Again, earthquake happens here, and we can measure the seismic waves and how they bounce back off of the liquid and solid inner core and outer core and mantle. So there are 3 types of rocks: igneous, sedimentary, and metamorphic. I'm going to go through each one of these and what they mean and how they're formed. But knowing about rocks tells us how it was formed, how it will break down or weather. We're going to spend a whole chapter talking about weathering and mass wasting. The first type of rock, igneous, is molten rock that cools. That is most of the crust of our planet. There are 2 types of igneous rock. There is intrusive or plutonic, and that is when magma cools above the surface. So if you look at this lava flow right here, it is cooling above the surface, and I'm sorry, I got that backwards. Intrusive rock is cooling below the surface over here. So you have a magma chamber over here. Some of it is cooling and is forming this intrusive plutonic rock. Extrusive or volcanic rock is this volcanic lava flow right here. That's when lava erupts and cools above the surface. And so lava is just magma that's above the surface. So here is a picture of some very new extrusive rock, igneous rock that I took in Hawaii. There was a lava flow that had covered this road. You can still see the sign there. So this is rock that I believe it's about 10 or 15 years old, and it cooled above the surface. It was a very slow lava flow that came down and then reached the ocean, but you can go there and walk on it in Volcanoes National Park, which is very cool, and I highly recommend it. The big difference when we're talking about igneous rock between intrusive and extrusive is that intrusive cools very, very slowly, often over many years, and then that makes it very hard, and it will weather away very slowly once it's above the surface. Extrusive rock cools very quickly within hours, and that makes it softer and weather more quickly. So you have 2 types of rock here, granite and rhyolite. One is intrusive, one is extrusive. They are made up of the same materials, but that cooling process, granite is very hard, which is why we like using it for things like countertops. Rhyolite is an extrusive rock, and it is much easier to break apart. So 2 rocks can have the same mineral composition, but be very, very, very different. And so this affects, again, weathering. So here is another landform from my vacation. This is Shiprock in New Mexico. And so this is a plug of a former volcano. So what you're looking at here is that magma chamber that then cooled. And so the original volcano, this is like a guess, but was something like this. And this was the intrusive rock that cooled very, very slowly. And this was the extrusive rock that cooled above the surface and was much softer. And so what happens here is this extrusive rock eroded away because it was much softer, and you're left with this much harder intrusive rock that will take a long, long time to erode. So extrusive rock signifies recent volcanic activity. Only intrusive rock remains from ancient volcanic activity. The next type of rock is sedimentary rock. And that's when sediment or little bits of rock and some other stuff get transported and deposited to a place, usually by water, but can also be by wind. Layers are deposited on top of older layers. And so you see here in at the end of a river and a lake bed, you're going to get this sediment that's going to continually pile up on each other and then be compacted. And then the pressure from the other layers, the upper layers, cements the lower layers into rock. Back. And so here you can see this is another picture from a vacation. This right here, these are former sand dunes. That then there was more sediment that piled up on top of it. It got compacted. So very often when you look at sedimentary rock, you can see very distinct layers. There are some other types of sedimentary rock that are made up of organic sediments, so not necessarily pieces of rock. They contain carbon. One great example of that is coal. Then there's also precipitated sediments, and those are sediments that settle in oceans that form solids. And so here's a picture of that, this limestone in New Zealand. At one point, the sea level was much higher, and these are sedimentary rocks that formed there. And so again, limestone is an example of that precipitated sediments. And the third type of rock is metamorphic rock. And so that's rocks that are pushed deep under the surface by moving plates. So you have two plates here. One is subducting under the other. You have this rock that's being pushed underneath and a ton of pressure that is pushing on this rock. And so from extreme pressure and heat, it gets morphed, ergo the name metamorphic, to change its form. So you look at the sandstone, which is a sedimentary rock, that when it's pushed underneath the surface by moving plates, extreme heat and pressure, it actually becomes quartzite. So this turns into this. And an important thing to understand about the rock cycle is that any type of rock can turn into any other type of rock. So the Earth is like constantly erasing itself and remaking itself. It's a little bit like a giant Etch-a-Sketch. And again, this is over geologic time, like very, 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 very long time. So here we have sediments that are compacted, turns into sedimentary rock, that then get pushed underneath from heat and pressure and become metamorphic rock, and then get melted and then come out and turn into volcanic rock. So again, over and over and over, they could become any other type of rock, and very, very, very slow process. Igneous rocks that occur in a series of lava flows or eruptions. And you can see here, that series of lava flows that then hardened above the surface. Sedimentary layers of rock are layers of sediment deposited on top of older layers. And so we have these strata, this is a sedimentary one. And what we know is that this rock is older than this rock. And that's just logical, right? Here's the older rock, new stuff gets piled on top and piled on top and piled on top, and so the stuff at the top is newer. And that's true of this igneous rock as well, right? This lava flow here came out first, and then more flowed on top of it and more flowed on top of it. And so that's called superposition. And so it's the relative layering of rocks that tell us the age and geologic history. Just based upon what's on bottom and what's on top, we can understand what happened first, what happened second, what happened third. just looking at the distribution of surface rocks in the United States, so we have lots of sedimentary rocks. There used to be uh, big inland sea here. Underneath this, it's mostly igneous rock. We have extrusive igneous rock in the west from volcanic activity. Um, and what's really interesting is that Native Americans used to trade materials. Some extrusive volcanic rock is very, very valuable for something called flint knapping, making things like arrowheads and knives. And so we can tell actually how different tribes traded with each other depending upon the materials that we find in those locations. And the last thing that we're going to talk about is bedrock. Um, so we are our soil is sitting on top of bedrock, right? So where we have a lot of soil, we are sitting on a solid foundation. And so, if you are going to, you know, have to dig down to put in pylons for a bridge or something like that, you're going to have to dig down into that bedrock because that's what's going to hold on to it. So soil is really just partially made up bits of rock. There's an entire chapter of soil in your book, which I, for time, don't cover in this class. But if you want to know more about soil, there's a whole chapter that you could go to look more of that up. And studying soil helps us understand geology at that place, right? We can look at soil and see what it's made of, and see where it came from, and how that got taken there. And also, just a quick reminder that bedrock is also where Fred Flintstone lives. This is the end of chapter 13. And so the next chapter that you're going to do for this class is going to look at the internal processes.